Unit Operation Classroom. Today we are discussing correct statements about heat of reaction. My name is Shekhar Bhattacharjee. Which of the following statements regarding the heat of reaction is or are correct? So first, let us see what's the definition of heat of reaction. This is defined as, let's say we define a reaction something like this, where A, capital B, capital C, etc. are reactants, and small b, and small c are their corresponding stoichiometric coefficients, whereas capital D, capital E, capital F, etc. are the products, and small d, small e, small f are the corresponding stoichiometric coefficients. So heat of reaction is defined as the summation of the heat of formation of each of the species of the products multiplied by their corresponding stoichiometric coefficients minus of similar thing for the reactants. That means the heat of formation of each reactant multiplied by the corresponding their stoichiometric coefficients. So this can be just says that the heat of reaction is equal to total heat of formation of products minus total heat of formation of reactants. And of course, the above relation can be also shown using Hess's law. I'm not going into the details. That heat of reaction is equal to total enthalpy of products minus total enthalpy of reactants. So if we look at the option D, it says it is the enthalpy change for a process in which the stoichiometric quantity of reactants at a temperature and pressure, so of course this is defined for a certain temperature and pressure, complete reaction in a single reaction to form products at the same temperature and pressure, which is basically the same thing here. So this definition is of course true, and this is a standard definition of the heat of reaction. So option D is true. Now let us take option A, B, and C individually. Option A, of course, we are taking now the endothermic reaction. For endothermic reaction, it says that the heat of reaction is positive, which is very true. That so what really happens is that for the endothermic reaction, the total enthalpy of the product is greater than the total enthalpy of the reactants, of course, right? So what happens that if this has the reactants have less enthalpy than the products, of course. So what happens that we have to supply energy to the reactant during the reaction to form the products, right? So that's what happens. So delta H0 reaction is positive since this is higher than this one. So this is positive. Heat of reaction is positive. Enthalpy of the products, this one, is greater than the enthalpy of the reactants, which is this one. And of course, heat is absorbed. So we actually supply heat during the reaction and this one to form the products because this has a higher enthalpy. So these are all statements are true for an endothermic reaction, right? So heat of reaction for an endothermic reaction is positive, which is option one, that is true. So if we just go for the other one, exothermic reaction, it is negative. As you can see intuitively, for an exothermic reaction, of course, we see that enthalpy of the product is less than the enthalpy of the reactants. Enthalpy of the product is less than the enthalpy of the reactant. So what happens that this has a higher enthalpy than the product, so the excess enthalpy will come out, and that is basically exothermic reaction. So heat is released during the reaction. So system loses energy. So as we see, enthalpy of this one is less than this one. This one is less than this one. Okay, so delta H0 reaction is negative. Okay, enthalpy of the products is less than the enthalpy of the reactant. So heat is released during reaction and the system loses energy. So option B is true. And option C is just the opposite of option B. So that's why it's false. Because it says for an exothermic reaction is positive. So it's just the opposite of this one. So this is false. So option A, option B, and option D are true. Just like other problems, we try to give you a practical application of each problem. So this problem has tremendous application in industry, that we have to have an idea about the enthalpy of the product, enthalpy of the reactants, as well as whether it's an exothermic or endothermic reaction. Let's say for like the formation of ammonia by the Haber-Bosch process, this is a highly exothermic reaction. So the proper knowledge of the heat of reaction is required for design of multiple bed reactors with intercooling, calculate the reactor heat duty, and design of cooling coils, etc. Similarly, if it's an endothermic reaction, let's say for steam methane deforming reaction, which you have seen before, where of course methane reacts with steam in presence of catalyst to form carbon monoxide hydrogen. This is a highly endothermic reaction. That's why the reactor is placed inside a furnace, and there's a continuous supply of energy, external heat to this particular reaction, to the reactant, to form the products here.